Please join. Can you see me? Can you see the blackboard clearly? Tell me. Hello, Shubhadeep. Good evening. So, please tell me. Can you see the board clearly? Hello. Can you see also board? Can you see the board clearly? Okay, thank you. So today I will discuss linear transformation. Linear transformation. Suppose let V be and W be two vector spaces, then W is called linear transformation. Yes, only one good evening. If E V1 curve plus V2 curve E V1 curve plus E V2 curve for all V1 curve V2 curve belonging to V, and two T lambda V1 V curve, where lambda is a scalar multiple for all lambda belonging to R and V curve belonging to. So this is the definition of linear transformation. So I take some example. Example one, E into V, where E V current equal to zero current for all V current belonging to V. Check that this is a linear transformation. Just see these two properties. So since take any two vectors in V, say V1 curve and V2 curve, according to this definition, this gives zero curve. Again, in V1 curve, this is again a zero curve. In V2 curve, this is again a zero curve. So in V1 curve plus the V2 curve equal to zero curve plus zero curve. This gives zero curve, which is equal to T V1 curve plus T V1 curve plus V2 curve. Yes, Sompun, this is the operator. This is the map. Okay, function self operator. And so one is satisfied in this case. Similarly for two, lambda v1 curve, lambda v curve. V curve is any vector in V. Since there is a vector space, so lambda v curve again belonging to V. According to this definition, this should be zero curve. And since lambda v curve, v curve is zero curve, so lambda into zero curve again this zero curve. This to imply T lambda v curve equal to lambda T v curve. Hence, this is a linear transformation. Hence, this is a linear transformation. Transformation from D to T. So next example, where okay, so take two vectors V1, V2. Take two vectors V1, V2 belonging to V. Then E V1 curve plus V2 curve, this gives V1 curve plus V2 curve. This is equal to V1 curve plus V2 curve. Again, for any two V1 curve equal for any V curve belonging to V, lambda belonging to R, T lambda V curve. This gives lambda V curve equal to lambda T V curve. Hence, T is linear transformation. Example 3. Example 3. If V to V, here I take V like Rn to Rn, where M less than equal to M, then x1, x2, xn equal to x1, x2, xn 0, 0, 0. If I add n minus n0, this means this belonging to Rn. So this gives a linear transformation. You can check the same way to see that this is a linear transformation. Check E is linear transformation. This is called natural inclusion. Natural inclusion of Rn R. Okay. Into R. Rn into R. Next example. Example 4. P Rn into Rn where n greater than equal to. Then define T as check that T is linear transformation. This is also another one. This is called natural projection. Of what? Natural projection of Rn. Why it is on onto Rn. Another example. R2 R, where T x equal to x square, x belonging to R. Check that whether is it linear transformation. This is another homework. Next example, example 6. T R squared to R cubed, where Pxy is equal to xy. Third component, product of xy. For example, if you take 1 2 vector, then I think it is better to write 2 3. Then it should be 2 3 into 3, that means 2 3 6. Okay. For example, so check that, or question is it linear transformation? Oh, just see the property addition P x curl plus y curl is tx curl plus py curl, and another is lambda tx curl, lambda t x curl. If these two things are satisfied, then there is a linear transformation. Otherwise, not. Another example, example 7. T R square to R square, where T xy equal to x comma y plus 3, then check that, or is it linear transformation? Example 8. For given v curve, this is a fixed vector. For given v curve, this is a fixed vector which belonging to v, then v curve to v, v to v, where v curve equal to x curve plus v curve for all x curve belonging to. Is it a linear transformation? If not, if not, then find value of the curve such that he is linear transformation. So question is it a linear transformation? If this is not a linear transformation, then find the value of v such that it is a linear transformation. This is another homework. Okay. So somebody tell me, can I wrap this portion? Can I wrap this portion? This part? Tell me. Please tell me. Can I wrap this part? This part? Okay, thank you. Let V and W be two vector spaces. So I denote the null vector of V by O V card and null vector of W by O W card. These two are not same. Okay. So for that reason, I denote the null vector of V by O V card. V is the suffix. V is the suffix. W OW curve is a null vector of W. Now claim is, suppose I define a linear transformation E to W, then claim T OV curve, this gives OW. So OV curve, OV curve, this gives OV curve according to the linear transformation. OV curve, OV curve plus OV curve. So since this is the linear transformation, this gives OV curve plus TOV curve. This is equal to OV curve TOV curve. So TOV curve plus TOV curve. I add both sides by minus TOV curve equal to TOV curve plus minus TOV curve. So using associative property, TOV curve minus TOV curve. This gives, since X curve belonging to V, then TX curve belonging to W. So X curve TOV curve is belonging to W curve and minus TOV curve. W curve, W is belonging to W and minus TOV curve is again belonging to W, but minus TOV is a inverse of TOV. This gives null vector. This null vector belonging to W, so this should be TW. So this again equal to TOW curve or TOV curve is in same argument. This gives OW curve equal to OW, and this says again TOV curve, because something plus null vector gives X curve plus O curve gives X curve. So this is TOV curve equal to OW. Hence this claim is true. Yeah. Let basis of a vector space V denoted by V1 curve, V2 curve, অঙ্কন C. I think this is obvious. Null vector plus null vector gives null vector. Okay. So now, since this is a linear transformation, T is a linear transformation. According to the linear transformation, we know Tx curl y curl equal to Tx curl plus Ty curl. So T OV curl plus OV curl, this gives T OV curl plus T OV curl. And this is equal to, I use T both sides, so this is equal to T OV curl. So this is again equal to T OV curl. Clear? Tell me, Uncle response yes and no up to that. Uncle or anyone tell me up to that. Okay, thank you. Now I add this minus T over curl both sides. Okay. Then use associativity property, that is x curl plus y curl plus z curl. This gives x curl plus y curl plus z curl. I use this thing. Okay, Anirban, tell me. Can you see this thing? Suraj, I use associativity. For this step, I use associativity property. Okay. Then minus T O V curl inverse element of additive of T O V curl, and these two vector belonging to W. Why? Because T is through linear transformation. Through linear transformation, we get a vector from W using V. This is the operator. So if x belonging to V, then Tx curl belonging to W. So these two vectors both belonging to W. Hence we get the null vector of W, that is OW. Now it is okay or not? Tell me. Now it is okay, Ankon. Can you see the code clearly? Ankon, I'm asking you. Okay. So this thing is clear. So T O V curl and minus T O V curl both belonging to W. Okay, Ankon, both belonging to W. So this gives a T O V curl minus T O V curl. This gives a null vector. The null vector which the null vector of what? Null vector of W. So I use OW curl. And similarly, this right hand side also gives null vector of W, which is OW curl. Therefore, something TOV curl plus OW, this gives TOV curl, and right hand side OW curl. Hence, TOV curl equal to OW curl. This means this claim is true. Clear on code? Tell me any, if you have a still have a doubt, tell me. I'm waiting. If you have any doubt, please tell me. I see only 13 people are there. Please join. If only now it is 14. I think your strength is around 50, but I see only 14 people attending the class. Present. Let the basis of V is V1 curve, V2 curve, Vn curve. Let W1 curve, W2 curve, Wn curve be any vector any vectors may not be unique, may not be unique. End of. So I take a linear transformation T V to W. Define T V curve equal to I from 1 to n lambda I W I curve where the curve belonging to V this imply the curve equal to sum over I from 1 to n lambda I V I curve take lambda equal to 1 and lambda j equal to 0 for all j not equal to I. Claim is, I think I erased this portion. So first I take a basis of V, V1, V2, Vn. Then I take some vector W1, Wn in W. V and W both subspaces, both are vector spaces, these two are vector spaces. Now I define operator TV curl such that TV curl equal to I from 1 to n lambda Wi. That means TV curl is vector belonging to W which can be written as a linear combination of this vector w1 to wn, where V curl be any vector in capital V. This implies V curl equal to sum over I from 1 to n lambda vi. Now, if we take lambda equal to 1 and lambda j equal to 0 for all j not equal to I, then my claim is T is a linear transformation V to W is a linear transformation from V to W, and it is unique. Okay. So now I am going to prove T is a linear transformation and this linear transformation is the unique. If I define T as follows. So, proving linear transformation, we take two vector x curl and y curl both belonging to V, and V1 to Vn is a basis of V. This implies x curl can be written as a linear combination of the base vectors in basis. So that is equal to sum over I from 1 to n del I vi curl and y curl also written as a linear combination of v1 to vn, that is del I star vi curl. And since these two vectors x curl and y curl are not equal, any two vector, that means these two are not equal. So the represent, since we know any vector represented by basis is unique, so at least one here delta and delta I dash not equal. According to the definition, this is the definition of T, then X curl should be sum over I from 1 to n del I wi. And according to this definition, Ty curl should be sum over I from 1 to n del I star wi. Now, x curl plus y curl, this is equal to I from 1 to n del I plus del I dash vi curl. So according to this definition, Tx curl plus y curl is equal to del I plus del I dash wi curl I from 1 to n. So write this as I from 1 to n li wi curd plus I from 1 to n li dash wi curd. So this is equal to t x curd and this is equal to plus ty curd. So first property is satisfied. Now for the second, lambda x curd is equal to lambda I from 1 to n li vi equal to sum over I from 1 to n lambda del I vi curd, then t lambda x curd according to the definition of t, 1 means Subhrajit Das, you say 1 1. What do you mean by 1 1? Are you mean by 1 to 1 transformation? Actually, I do not want to show that whether it is a 1 to 1 or not. I just define a function is t as follow, which is a linear combination of some vectors of w. Because t v because is belonging to w, and I define t v curl as a linear combination of some vectors. This may not be unique. It may not be a basis. This this is the curl is a linear combination of this vector. If you define this t curl as follow, and this imply v curl equal to sum over I from 1 to lambda vi curl, where v1 v2 vn is the basis of v, and if lambda either 1 and other portion is 0, in that case my claim is T is a linear transformation, and if it is linear transformation, then it is unique. This is the proof. This is my claim. For proving this claim, first I prove that this is a linear transformation. For see that this additivity property hold tx plus ty tx plus y curl equal to tx plus ty curl. Then for the second property, so according to this definition, lambda x t lambda x curl equal to I from 1 to n lambda del I wi curl. Just I use this definition. So this again, this thing as del I wi curl, and this gives lambda t x curl. Hence, this is the linear transformation. Hence, this is a linear transformation. Yes, the question is clear now. Actually, I misunderstanding at the first place. Sorry. No, it's okay. Shubhuji, this is the learning stage. Huh? So don't say sorry. It's okay. No problem. So this is now you see that T is a linear transformation. If you define T as follow, then we see that T is a linear transformation. Clear? Up to that, clear? If you have any doubt, please tell me. Anybody, if you have a doubt, please tell me. Before going to the next step means, now I want to prove T, if we define T as follow, then T is unique. This transformation is unique. For going to the next proof, first tell me, up to that, is it clear for you or not? Can I repeat once again? I have no problem. Please tell me. Can I repeat once again? Ankon. Okay. Ruchira, you say, oh, yes, sir, clear. Thank you, Ruchira. So, up to that, this is clear. It is a linear transformation. For now, for uniqueness, so for uniqueness, I define another transformation, linear transformation, denoted by T dash from V to W. Is another linear transformation linear transformation defined as TVI curve equal to WI curve, where I from 1 to n. So now, for any vector, the curve belonging to V, this implies the curve can be written as a linear combination of the basis lambda vi curve. Since this is a linear transformation, then T dash v curve, T dash sum over I from 1 to a lambda vi curve, using property 1 and 2 simultaneously, we can write this as okay. Sorry, this is a T dash. Okay, please correct this. This is a T dash, not T. So, according to this definition, this is equal to lambda I wi curve, and I already defined this gives T curve. Hence, these two operator or these two linear transformation equivalent. You do not give when you use operator, you should use equivalent instead of equal. If you use equal, this is wrong. This is not a numeric thing. Okay. Clear? If you have any doubt, please tell me. Before going to the next part, please tell me if you have any doubt. So, before going to the next part, please tell me if you have a doubt. Please tell me if you have any doubt. I'm waiting. Can I wrap this portion? The left hand side. Can I wrap the left hand side portion? Let T is a linear transformation from V to W, where V and W be two vector spaces. Let basis of V, V1 curve, V2 curve, Vn curve, and basis of W is equal to W1 curve, W2 curve, Wm curve. This M, N, and M may not be same. Okay. Now, TV1 curve, this vector belonging to W. This means TV V1 curve can be written as a linear combination of the basis of W, and denote this by A 11 W1 curve, A 12 W2 curve, A 1 M WN. Similarly, TV2 curve written as a and lastly therefore this implies so this implies we can write this as and we denote in WV and I denote this matrix by capital A and this equal to denote this matrix by A transpose which is equal to A11, A21, A1, A12, A22, A N2, A1M, A2M, A N M, and this matrix is associated with associated with t with respect to with respect to t and w. So from here we see that linear transformation is nothing provides a matrix. That if you have a matrix, you can easily define linear transformation. This is a definition of a matrix. Actually, from V to W, this linear transformation is nothing but a providing a matrix. Actually, so this is the n cross n matrix. Actually, this is the proper definition of matrix. Actually, every linear transformation there is a matrix, and the dimension of the matrix is in. This is the dimension of W. A. This is the dimension of V. So I illustrate this through an example. Suppose we define linear transformation actually R squared to R squared where Txy x plus y x minus y. So this is your V and this is your W. So E1 curve, E2 curve, I already defined this E1 curve, E2 curve. These are the canonical basis. This is the canonical basis. So I take a canonical basis E1, E2, which is E1 curve, E2 curve. So the basis of R square. So E1 curve means 1, 0. So this should be 1 plus 0 minus 1 minus 0, that is 1, 1. And we write again E1 curve, E2 curve are the basis of R squared. So write this as 1 E1 curve, 1 E2 curve. Another E2 curve, this is equal to E2 curve means 0, 1. So this is 0 plus 1, 0 minus 1. So this gives 1 minus 1. So 1 E1 curve plus minus 1 E2 curve. Then here I simply write A instead of A in B. You automatically realize this A means this. M VW within bracket T. So M here, M is first first row is 1 1 and second row is 1 minus 1. Second row. So this is an associated matrix. Similarly, if you change the order of a basis, instead of A1 curl, E2 curl, in that order, if you take E2 curl, A1 curl, then what happens? AT per, I define this matrix by A transpose. MT, I define MT as a transpose, A transpose. And this is this matrix. No, this matrix is a associated with T with respect to V and W. Okay, and this name VWT comes from this because TV1 curl is a vector which belonging to W. This can be written as a linear combination of this A11 W1 curl plus A1 to W2 curl plus W dot A1 in Wn curl. Similarly, TV2 curl, Tvn curl, and you can represent this in matrix notation. And I denote this matrix by A, and I denote the associated matrix T with respect to V and W by AT. Okay, Uncle. So now my job is I take different example how to find MT. So if you take E1 curl, E2 curl, your aim is this. If you change the order of a vectors in a basis, instead of E1 curl, E2 curl, you take the order E2 curl, E1 curl, then you see that T E2 curl, this gives 1 minus 1. So this is 1 E1 curl minus 1 E2 curl T E1 curl 1 E1 curl 1 E2 curl. So here the associated matrix M is, this is the first row 1 1 and this is the second row minus 1 1. Now you see that these two M are not same. So from this we can conclude that order of a basis, the order of a basis, it depends on the structure of it depends on order of a basis. So Uncle, can you tell me if you have any doubt? Tell me. Uncle, are you understand this things T V1, V2, Vn, this vector equal to A W1, W2, Wn? Yes, Suraj. Exactly. This is a transformation matrix. Actually, this is a matrix. Actually, matrix, every matrix give a transformation, linear transformation. Okay. This is the definition of a matrix. Actually, linear algebra, vector algebra, and linear transformation basically is a bridge between vector algebra and matrix algebra. you can easily through a matrix you can prove the result of a vector algebra in a matrix algebra. Even if from using linear transformation, some results of a matrix algebra we can prove by vector algebra. This is the linear transformation is a bridge between linear vector algebra and matrix algebra, and combining these two things is called linear algebra. Okay. So Ankon, I am telling you, please tell me if you have any doubt. Can I take another example? Can I take another example? I think if I take another example, then it is more clear. If you take from t r square to r, and if you use same linear transformation, but I take another basis. Suppose instead of canonical basis, if I take 1 1 1 0, you can check that this is independent. A maximum number of independent because dimension of R square is 2, so the number of vectors in a basis in R square should be 2, and this gives a basis of R square. If you take this basis, okay, is a basis of R square, I denote this by U1 curve, V2 curve. Now, V1 curve, according to the definition, see, this is a x and this is y. Okay, so V1 curve is a 1 1. So according to definition, x plus y means 1 plus 1, and x minus 1 that is 1 minus 1. So this is 2 comma 0. Okay, and if you take this is the basis of R square, here R square is V, and I take another basis of R square, say 1 1 1 minus 1. So this is W1. Can you see this thing? W1 curve, and this is W2 curve. This gives basis of W. So now this is nothing but a 1 1 plus 1 minus 1. Okay. So this is your A11 W1 curve plus A12 W2. Okay, Uncle. Where A11 equal to 1, A12 equal to 1. Now, V2 curve. This is your x, this is your y. So x plus y gives 1, and x minus y gives again 1. So this is 1 into 1 1 plus 0 into 1 minus 1. So where A21 equal to 1, A22 equal to 0. So your associated matrix is, that is transpose, the first row is A11, A21, that means 1 1, and second row is A1 to A2 2. That is 1 0. Where again here we also check that if I change the order of a basis, instead of V1 V2, I take V2 V1. That means 1011. That is V2 V1. So in that case, this is your A1112, and this is your A21, A22. So another aim is 1 1 1 1 0 1. Sorry, 1 1 1 1 first row, and second row is 0 1. So again we see that these aim and aim stars are not same. So if you change the order of a basis, then your aim also change. So it is very much depend on your order of a basis. Clear? So if you have a linear transformation, I think it can easily be able to associate it, be able to find associated matrix. Now, please tell me if, if you have still doubt, if you have if you face still problem, then tell me. I will explain again. I have no problem. Please tell me. Please tell me. Take your time. Then tell me if you have a doubt. Yes, Saniva. Of course. Of course, it depends on the order of the pieces. Because if you know the matrix, then you can automatically know the linear transformation. Okay. So can I continue? Please tell me if you have a doubt. Yes and no. অনির্বাণ ফুটজ অঙ্কন দিশারি শুভদীপ, tell me. Okay, thank you. So let T be a linear transformation from E to W. it will be a linear transformation from V to W, and U and 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 there is another transformation U V, another transformation. Bomb W to Z. Let beta is the basis of V, beta dash split with V, split with basis of W, split V double dash. These are the bases Z. Now let A be a matrix of T relative to the pair dV dash. Similarly, let B be a matrix of U relative to the pair B dash B double dash. Therefore, if alpha current belonging to V T alpha current this gives because this is belonging to W, so it can be represented as a linear combination of bases. So I write this notation. So this gives it a so I think it is better to write in that way also. Forget about this notation. Say you compose T, compose alpha curve, where alpha curve belonging to V. Now I take a transformation into P alpha curve. This gives U P alpha curve. So I think it is better to write alpha J curve, alpha J curve, alpha J. So now P alpha J belonging to where? Belonging to W. So we write this as a linear combination of A K beta K curve K from 1 to M. Then I write this H. So since this is a linear transformation, so I write it as again U beta K curve belonging to what? J. So this can be written as a linear combination of the vector in the basis of Z, that is gamma S. So I write this as I from 1 to K gamma curve. Okay. Then interchange the summation. Is better to write in that BIK KK. So this is, if you look at this, BI1, B, BI1, BI2, BIN is vector A1J, A2J, AN. So this is a jth column of matrix A and this is ith row of matrix B. So this is Bi Bi, and denote this row vector by Bi dot, Bi dot, and column vector by A dot J gamma J, gamma I. So this is a scalar. I denote this by Cij gamma I card. So this gives Cij Bi dot A dot J for all I from 1 to T, J from 1 to J from 1 to N. So C, the matrix, is Ij the limit of this. This is nothing but a product of a two matrix whose order E cross M, M cross N. This is M cross N. So this gives product of a two matrix. Okay. So please tell me if you have a doubt regarding this derivation. I will explain you again. Next definition, kernel of T. Oncon. You need to please expand the left side of board. Okay. Suraj and this means G effects. Yeah. So these things are same thing. Okay. So that's why I write U T alpha J. T alpha J means T alpha J belonging to where? Belonging to, I forgot I think it's a W. W. T alpha J belonging to W. So T alpha J can be written as a linear combination of basis of W. The basis of W are, I assume, beta 1, beta 2, beta n. So this can be written as a linear combination of basis of W. Since this is a linear transformation, U is a linear transformation. So using property 1 and 2 simultaneously, you get this. Again, U beta k curl belonging to set Z is a vector space, and I assume the basis of a Z is a comma to gamma p. So this can be written as a U beta k curl can be written as a linear combination of a basis of set So this is now I interchange this sum. These two things are same. Just interchange it because this is independent of I. So I take this sum first and then this sum, and you see that just look at this portion. This thing are same thing of this multiplication of these two vector. One is a row vector, another is a column vector, and this is nothing but a ith row of B matrix, and this is nothing but a j column of a A matrix. So Cij is nothing but a product of ith column of a B matrix and jth ith row of a B matrix, jth column of a A matrix. So hence matrix C is nothing but a product of a two matrix B and A. Okay, Ankon Anirban, Suraj, now clear? Tell me. Tell me. Thank you. Ankon, what is your opinion? Now it is clear or not? Anirban, third line. This means this. Ankon, third line means this line. Just tell me, am I right or not? Third line means you want to mean this line. Yes or no? Okay. Okay. So you know the property, two property, x square plus y square equal to t x square plus y square. This is the definitions from linear transformation. This comes from definition of linear transformation. So using these two properties simultaneously, you can get this thing. This is the scalar thing. For example, suppose so using this property, so repeat this process, then you get this thing. If you repeat this process, then you get this thing. Now clear, uncle? Tell me. Tell me, uncle. Okay. Now kernel of T, to define kernel of T is a collection of vector vector which belonging to vector space V such that T vector equal to 0. This is nothing but a system of homogeneous equation. or error space. So you can easily check that kernel of T is a subspace of V. Kernel of T is a subspace of V. Now I denote gamma T is a dimension of kernel of T, which is called nullity of T. Now image of T, this is a collection of vector W. So one thing I want to say, I have a two vector spaces V and W. I use linear transformation T, V and W. Under this we define kernel of T and image of T. So W, this W belonging to W curve belonging to W, where W is a vector space, such that there exists V curve belonging to V curve belonging to V, such that V curve equal to W. So I take an example. Suppose I transform R cube to R, where T defined as XYZ, X plus Z, X plus Y plus 2Z, 2X plus Y plus 3Z. So if this thing, this vector belonging to kernel of T, then this should be 0. So this implies X plus Z 0 curve, X plus Z equal to 0, X plus Y plus 2Z equal to 0. Two X plus Y plus 3Z equal to 0. So this means X is equal to Y equal to minus Z. So kernel of T is a collection of vector X, Y, Z, such that X plus Y, sorry, X is equal to Y minus. So another representation is lambda 1 1 minus 1, where lambda belonging to R. Sorry, I erased this line. This thing is not visible. So another representation is 1 1 minus 1 lambda into 1 1 1 minus 1 where lambda belonging to R. So yes, Uncle, null space and kernel are same thing. So gamma T, that is dimension of kernel of T here, equal to 1. So now so kernel and error space are same thing. Null space, kernel and null space are same. Null space means what we mean by null space. Null space is a particular space. You can say error space or the space consisting of the solution of homogeneous equation. These are all same thing. These are all same thing means in particular, uh, if you consider Rn, then these things are same. Okay. So this actually system of homogeneous equation, actually the set of a solution of a system of homogeneous equation is example of a kernel. Now x plus z, x plus y plus 2z, 2x plus y plus 3z equal to w1, w2, w3. When we simplify x plus z equal to w1, x plus y plus 2z equal to w2, 2x plus y plus 3z equal to w3. So this gives w1 plus w2 equal to w3. So this means w1, w2, w3 Vishali, dimension is simple thing. Actually, I express this vector. Actually, kernel of T consisting of the vector of R3, which satisfy the condition that x equal to y equal to minus z. So x is equal to x, y, z. So this thing is equal to x. See, since x equal to y, so I replace y by x, and since z equal to minus x, so I replace z by minus x. So this thing is 1 1 minus 1. Hence, kernel of T is space generated by only one vector, that is 1 1 minus 1. So the basis of kernel of T consists of single vector, that is 1 1 minus 1. Hence, the dimension of T is 1. Here, Dishari, understand? Please tell me. Are you understand what I want to say? This is the process. Similarly, here, Dishari, please tell me. Okay. So this is equal to W1, W2, and W3 is nothing but a W1 plus W2. So W1 101, W2 011. So image of T is a collection of vector W1, W2, W3, where W1 plus W2 equal to W3. So another representation is collection of vector 101 plus W2 011, where W1, W2 belonging to R. So hence dimension of image of T, which is nothing but a rank of T, this is 2. So therefore, dimension of R cube is generally V is equal to dimension of rank of T, rank of T, and nullity of T, that is normal. So now I am going to put this part generally. So please write. Suppose, can I erase this portion? I think I can erase it. So suppose, so result P is a linear transformation from V to W, where V and W are vector spaces. Linear transformation from V to W, where V and W be two vector spaces, then the result then dimension of V, this is equal to rank of T plus nullity of T. So assume x1 curl, x2 curl, x is curl, is create basis of kernel of T. This means T xi curl equal to 0 curl for all I from 1 to S. Since Kernel of T is a subspace of V, so we can add x s plus 1 third to s x in curd such that x1 curd to xn curd be a basis of V, be a basis of V. Now we want to put that T x plus 1 third to T xn curd be a basis of be a basis of image of. So proving this, we need to prove this set is a set of independent vectors as well as this set also generate any vectors in image of T. Suppose V be a vector belonging to V, then V can be written as a linear combination of the basis of V, that is x1 x2 xn. So the V curve belonging to image of V, image of T. So T V curve, if I take T V curve, T is, since T is a linear transformation, so this is equal to or T V curve equal to since the xi curve, 0 curve for all I from 1 to s. Hence, generating set of Now set since t is a linear function, so I write this as so this means this vector gamma s plus 1 x is plus 1 gamma n xn are belonging to kernel of T, belonging to kernel of T. Hence, this vector can be written as a linear combination of basis of kernel of T